Hello, and welcome to the Aqueous Equilibria and Titrations lecture from Chemistry 1412 with Dr. Elizabeth Bell. Before we get started, I'd like to review some vocabulary that relates to titrations. A titration is done with a volumetric burette and an Erlenmeyer or conical flask. The liquid which is put into the burette is called the titrant, and its molarity is known. The liquid in the flask is called the analyte, and its molarity is unknown. Using the volume delivered from the burette into the flask of the titrant and its molarity, the unknown molarity of the analyte can be calculated. The volume of analyte used is also known. If you plot the pH as a function of the volume of titrant added, you will have a titrant curve. There are many different types of titrations. Each one has its own particular shape to its titrant curve. The first type of titration we will look at is the titration of a strong acid with a strong base. Notice that the pH value at volume equal to 0 is quite low, at or under pH equal to 2. This indicates you are beginning with a strong acid in your flask. As a strong base is added, the pH very slowly starts to creep up in value until just before it reaches its equivalence point. The equivalence point is when the moles of base added is numerically equal to the moles of acid in the flask. As the titration reaches its equivalence point, the pH shoots up wildly. Very quickly after this, the pH curve flattens back out, and it ends with a pH that is very high, at or above pH equal to 12. The high ending pH value indicates that the titrant was a strong base. There is one last item of interest. In the titration of a strong acid with a strong base, the pH at the equivalence point is equal to 7. The next type of titration we will look at is the titration of a weak acid with a strong base. Notice that the pH value at volume equal to 0 is low, but it is greater than pH equal to 2. This indicates you are beginning with a weak acid in your flask. As a strong base is added, the pH very slowly starts to increase in value with a larger positive slope than the strong curve showed, until just before it reaches its equivalence point. Again, the curve shoots vertically up in pH value at the equivalence point. Very quickly after this, the pH curve flattens back out, and it ends with a pH that is very high, at or above pH equal to 12. The high ending pH value indicates that the titrant was a strong base. The pH of the equivalence point of a weak acid with a strong base will be larger than 7. It is possible to identify the type of titration occurring from its unlabeled titration curve. You'll need to notice at what pH value the curve begins and ends. If a titration begins at a pH equal to or lower than 2, then the analyte is a strong acid. If the titration ends at a pH equal to or greater than 12, then the titrant is a strong base. If the pH begins at a level greater than 2 but less than 7, the analyte is a weak acid. If the pH ends At a level less than 13, less than 12, but greater than 7, the titrant is a weak base. If the titration begins at a pH equal or to or greater than 12, then the analyte is a strong base. If the titration ends at a pH equal to or lower than 2, then the titrant is a strong acid. If the pH ends at a level greater than 2 but less than 7, the titrant is a weak acid. If the pH begins at a level less than 13 but greater than 7, the analyte is a weak base. There is one other clue to be gotten from the curve. Look at the pH value at the equivalence point. If the equivalence point is equal to 7, then it is either strong or weak. The starting and ending values tell you which. If the equivalence point is greater than 7, then it was a weak acid with a strong base. If the equivalence point is less than 7, then it was a strong acid with a weak base. When you have a titration that is weak-strong or weak-weak, there is a region between the beginning of the curve and the equivalence point in which the line is changing slowly with volume. This is the buffer region. The Henderson-Hasselbalch equation can be used anywhere in this region. Once you have reached the equivalence point, the buffer capacity has been met, and the Henderson-Hasselbalch equation is no longer applicable. Thank you for joining me for this mini lecture on titrations from our Chemistry 1412 class with Dr. Elizabeth Bell. Please go to Sapling at this time and complete any of the associated assignments. I encourage you to ask questions. I am happy to help. Bye.